I'm Becky Adams-Selin. I'm a senior manager and scientist at Atmospheric and Environmental Research, a company based in Lexington, Massachusetts. I work in the R&D division, which essentially uses federal funding to do research and then hopefully publish the results, much like a government lab would. My research involves looking at how the hail moves within the storm and trying to model that. I've been excited about thunderstorms ever since I was 6. So being able to go chase the thunderstorms was kind of a dream come true. In specific, what interests me about hail is there is so much uncertainty and there are so many interesting little pieces to it that you would think maybe isn't that big of a deal, but it turns out it's a giant deal. There's just so much uncertainty to it that even small changes, things like assuming the hailstone is rough instead of smooth, this seems like such a minor thing, but it can completely affect how fast it falls, which that affects how long it's able to stay aloft, that affects how big it's able to grow. Like it's just this mushrooming cloud of changes and uncertainties that happen just from small little details. And I find that really interesting. And it ensures that I have job security because we're not going to be able to figure this out super quickly. My career path was a little bit untraditional. I went ahead and did grad school, my PhD at Colorado State with Dick Johnson. He was a wonderful advisor, and he was actually willing to be flexible to let me attend remotely. This was back in 2012, so remote attendance was not a thing yet. But yeah, I was able to attend remotely and still, live with my husband where he happened to be stationed with the military. And so I was able to still continue my career. And then I was able to secure a job with AER in the R&D division. And they also continued to let me work remotely so that, yeah, I could both live with my husband and now my kids, but still be able to research these things that have always fascinated me. Regarding UASs, I'm the lead principal investigator of the ICECHIP field campaign, in situ collaborative experiment for the collection of hail in the plains. This field campaign just happened back in May and June of 2025. And essentially it was the first comprehensive look at hail in the United States in 40 years. So we were due. And we also got very fortunate that it was a highly convective year. We got all sorts of hailstorms. It exceeded our expectations. The ICECHIP field campaign was designed to look all the way from how it first starts in the storm, all the way to how it falls out at the ground and it impacts different things at the ground and causes damage. There are a lot of hail shapes. This is a somewhat famous hailstone that fell in Aurora, Nebraska. It was the U.S. record for a couple years. But yeah, as you can see, this is not a sphere in any shape or form. You get a lot of weird-looking lobes. The bigger the hail gets. Interestingly, one of my favorite shapes that we saw during the campaign, it looked kind of like a comet. It had what looked, maybe the original hailstone, and then, here's a bunch of ice kind of sticking off the back of it. And it actually, so it was very thin because it was cometish, but it was like 5.5 inches long. So it took out a windshield of one of our researchers, actually. But yeah, the shapes are widely varying. And was kind of opened my eyes to how much so. So yeah, ICECHIP really had kind of five different foci. The first being, hey, how does the hail move in the storm? How does it form? The very small scale, things like microphysics. How fast does the hail fall? Does it tumble? How does it melt? Real small scale stuff. Next foci, we shifted up a little bit to understand, hey, how does the hail move around in the storm? Because that's still kind of unknown, believe it or not. Then finally shifting back a little bit more, saying, hey, how does the environment around the storm affect how the hail moves around it and falls out, and grows? Next to last is the fourth one, and that is understanding, hey, when the hail falls out at the surface, what are its characteristics beyond just size? Typically we would get information from a hailstorm, like the Storm Prediction Center might retain a couple of reports of max size of hail at different points in the storm's lifetime. But we would want to know things like, hey, number one, multiple points along the storm's lifetime, all along the hail swath, so we know how it varies over the um, over the storm's lifetime and across the hail swath. And we know more than just size. Things like shape. It's usually not a perfect sphere. There's a lot of weird shapes that we just aren't aware of. Concentration, density, all things that we have no frame of reference for. And then finally, the fifth focus is radar, because using radar is our best technique, best method to be able to issue any sort of warning on these storms. So yeah, we really needed to. That's why the comprehensive nature of this was so important, that we could get all this radar data at the same time that we knew exactly what kind of hail was coming out of the surface, so we could have a real good idea of what hail forming in a storm would look like on radar and give us some new warning techniques. So where UAS fits in is actually in that fourth focus. That the UAS gives us a chance to look over a lot wider area than we humans can just drive along and see. Oh yeah, this is where the hail formed. With the UAS, they're able to go quickly, look over a wide section of area and say, oh yeah, the hail swath actually extends from here all the way up to here. And they can get to it faster than we humans could. And they can get there before it melts. So a hail swath is basically all the hail produced by a thunderstorm. So if you think about it, it's not just, oh yeah, here's this hail report here and this hail report here, but in fact, it's been produced over this whole, multi-mile stretch, both kind of horizontally over at one given time, but also over the storm's life cycle. And so being able to successfully simulate how wide is this hail swath, where should the hail have stopped and where should it have started, that's really key to being able to get it all right. You can get, obviously, the super big hail, that's important, but you want to know where all of the hail ended up. And the drone information will be key for that. We were mainly using the drone for hail observations after the storm had passed. So the ground team would deploy, we'd get out of the way, and then we'd wait for the storm to pass. And then as soon as the storm has passed, then they would launch the drone off the top of the SUV and drive up and down where ground team is collecting hail. They'd drive up and down and fly the drone to be able to see, oh yeah, this is the full extent of the hail swath. The drone can stay aloft for a while and be able to drive up and down and see, oh yeah, here's the hail swath here, and then let's maybe go, some different directions from where from that main path to be able to see how far things extend. This was kind of a first time for MUSAS where they weren't deploying in advance of the storm, doing more temperature profile seeking, but instead we're behind the storm, looking to come back and see hail afterwards. So yeah, it was new, but they adapted to it quickly. The key information with the drones was really being able to tell us how far the hail swath extended. Yeah, that's key for all sorts of information, because again, it sounds really simple, but we don't currently have any idea for what the shape and size of hail swath produced by a storm looks like. And so being able to know, oh yeah, this storm and these types of things on radar produced hail exactly here, that's really important to end goals coming out of ICECHIP. Things like, warnings that say exactly where the hail might be expected to fall and where it might be, big enough that it's impactful. That's information that you've got to have some sort of observations about that before you can try to make future predictions. I know there was also some plans to use drones to image the damage to the crops after the hailstorm came through. And that's real key because, number one, we still want to be able to connect hail characteristics to damage. Obviously, farmers can know that, hey, my crop isn't doing that well, but we want to know, hey, how big does the hail have to be in order to damage the crop? How much damage can you expect? Is it possible for it to recover if given the point in the life cycle of the crop, for example? Are there some pests or other potential viruses or insects that can come along and attack the crop if it's now hail damaged. Yeah, so yeah, these are all things that drones give us the capability to look at, because you can't see the um, entire area of the crop just by looking at it on the road. So we use the Raven, and it's a fixed wing drone. Um, and we picked that one because we wanted to have cover as much area as possible and be able to stay aloft as long as possible, because we're trying to see, hey, how big is this hail swath and how much can we be able to observe from it. Now, on the other hand, kind of the quadcopter style drones, those can also be useful, but it's much more dependent on the surface that the hail is on. If you're able to get a nice short grassy surface, you can use the quadcopter to take pictures and get you information about actually the size distribution of the hail at the ground. That, of course, is much more kind of a point based, because you can't go very far with those. You can, oh yeah, hey, everything is lined up. I've got a great surface. I'm here before the hail's melted, and conditions are such that I can actually launch this thing. So yeah, the quadcopter style drones, those are wonderful for kind of point based size distribution measurements, and you can get as many of those as you can. But the fixed wing, which we worked with the CU Raven team, that's to be able to cover more area, stay aloft longer, and be able to kind of get as wide a range of information as possible. We're kind of thinking about using drones to simply drop lab-created hailstones to understand some more technical details about how the hailstones fall, to be able to manipulate and do sensitivity tests. Again, it's a type of thing where drones give us the opportunity that we wouldn't have otherwise, because probably no one's going to let us drop hailstones out of their building 30 stories up. So that drones give us the opportunity to do some things that wouldn't be possible otherwise. So my best advice for researchers looking to work with the UAS team is just really, really work with them to understand what their capabilities are and then where they have limitations. Because it can be really easy for us novices to think something along the lines of, oh, well, I'll just go fly this drone into the thunderstorm. I'll find out where the hail is there. Like, well, no, there's actually, a very specific set of limitations, and that they have to follow, FAA guidelines and personnel guidelines and all these other things. We actually have been trying really hard to ensure that we're pretty tightly coupled with kind of the end users of our information, so that new research can pretty quickly transition to operations. So we have like a whole committee set up of end users from the National Weather Service, the Storm Prediction Center, but also insurance companies. I personally would love to see severe thunderstorm warnings come out with things. Well, number one, that the hail size in the thunderstorm warnings would be accurate, because we'd have some sort of idea from the radar. Oh yeah, this is what kind of hail size should come, because that's really difficult to determine now. But also things like, oh yeah, how much of this is going to fall? What's the concentration? Is it, one or two giant hailstones, or is it, a whole flood of golf ball hailstones? Because, that's pretty impactful. Things like density. Is it going to be soft and slushy, or is it going to be really hard and dense? I'd love to be able to see more information like that conveyed to the public.